Environmental Science, Chapter 17, Global Air Pollution, Ozone Layer, and Global Warming. Two of the most immediate global environmental threats humans face are the climate change caused by greenhouse gases and abnormally high incidences of ultraviolet radiation on the Earth's surface from destruction of the ozone layer in the stratosphere. Both are caused by the introduction of large quantities of human-produced gases into the atmosphere. Let's talk about ozone first. Ozone is an important natural component of the stratosphere. It's a pollutant in the troposphere on ground level, but protects us from radiation in the stratosphere. The ozone is concentrated in a layer 12 to 16 miles above the Earth's surface. It's formed when the high-energy ultraviolet radiation splits normal oxygen, which then reforms into ozone, and then forms back into oxygen again. So it's in what we call chemical equilibrium. It shields the Earth from receiving too much UVB radiation. Wavelengths of ultraviolet radiation are classified as either UVA or UVB, with UVA being the longest at 320 to 400 nanometers, that's a billionth of a meter, or UVB from 290 to 320 nanometers. The shorter the wavelengths in UVB means the higher the energy that they contain and the more damage they can do. UVB is the chief cause of skin reddening and sunburn, tends to damage the skin's more superficial epidermal layers, plays a role in the development of skin cancer, and has a contributory role in tanning and photoaging. Its intensity varies by season, location, and time of day. The most significant amount of UVB that hits the U.S. is between 10 a.m. and 4 p.m. from April to October. However, UVB rays can burn and damage your skin year-round, especially at high altitudes and on reflective surfaces such as snow and ice, which bounce back up to 80% of the rays, so they hit the skin twice. UVB rays do not significantly penetrate glass. If we watch this video, if I can move it,
the Earth is covered with a thin layer of gas we call the atmosphere. Atmospheric pressure decreases rapidly as we move away from the surface. In the region known as the stratosphere, far above the troposphere in which all our weather occurs, the atmosphere is very thin. Here, short wavelength, high-energy radiation from the sun causes dissociation of oxygen molecules. When short wavelength ultraviolet light strikes an O2 molecule, it dissociates into oxygen atoms. When an oxygen atom collides with an oxygen molecule, an ozone molecule, O3, may be formed. The O3 molecule that is formed has excess energy, the energy released when the oxygen atom combines with the oxygen molecule. If it does not get rid of that excess energy, it rapidly dissociates back into O2 and O. However, if the O3 molecule collides with any other species present, most likely an N2 molecule, it transfers the excess energy to this molecule and becomes stabilized. When solar radiation from the ultraviolet region of the spectrum strikes an ozone molecule, it may be absorbed, and the O3 molecule dissociates. The ozone cycle in the stratosphere involves formation of oxygen atoms and reaction of these with O2 to form O3. Stabilization of the newly formed O3 by energy transfer through collision, and dissociation of O3 by solar radiation. The ozone layer that is established in the stratosphere by these equilibria shields Earth's surface from the ultraviolet radiation that is harmful to living systems.
O3 here is ozone, and shortwave radiation is UVB. In the middle of the 20th century, compounds called chlorofluorocarbons, or CFCs, were developed as a new class of chemicals that were safe, non-flammable, stable, and unreactive. These chemicals were very useful for industry as refrigerants and insulators. CFCs were considered ideal for refrigeration, air conditioning equipment, non-toxic propellants for aerosol cans, blowing agents for plastic foams, and solvents and cleaning agents in the electronics industry. It turns out the stability of these CFCs in the lower atmosphere permits them to mix completely into the atmosphere and diffuse upwards into the stratosphere. In the stratosphere, where conditions are different, pressures are different, temperatures are different, ultraviolet radiation can break down the CFC molecules, releasing atomic chlorine. The chlorine atoms react catalytically with ozone, converting it back into normal oxygen. One chlorine atom may destroy between 10,000 to 100,000 ozone molecules before being washed out of the atmosphere as precipitate. This has done serious damage to the protective ozone layer in the stratosphere. Over Antarctica, because of the special wind and vortex conditions, every summer a huge hole in the ozone layer is formed. It was discovered in the mid-80s. During that time, researchers found and confirmed the existence of severe seasonal ozone layer depletion. The ozone depletion ranges between 50 and 100%. The ozone layer is also thinning in the northern hemisphere, although it doesn't form a huge hole, it's more like patches of holes. Excuse me. The hole forms over Antarctica in the winter because in the winter the stratosphere above the Antarctic continent gets colder than it does anywhere else on Earth. Temperatures frequently drop below 112 degrees Fahrenheit. In addition, Antarctica is also one of the windiest places on Earth. In May and June, strong winds in the stratosphere begin to blow clockwise around the continent. These howling stratospheric winds gradually form an enormous ring of moving air, called the Antarctic polar vortex. It swirls around and around, far above the land. During the winter, temperatures inside the Antarctic polar vortex fall so low that water vapor and several other types of molecules in the stratosphere condense into extremely small, icy particles. These icy particles in turn make up something called polar stratospheric clouds, or PSCs. When the sun sets in the Antarctic around the end of March each year, its disappearance marks the beginning of a long, dark winter. Once the last rays of sunlight have faded away, temperatures on land and on the air fall very quickly. In the stratosphere, high-altitude clouds that create the solar vortex begin to blow around the continent. Isolated from warmer air outside the vortex, the air inside gets colder and colder. Eventually, it is cold enough for the polar stratospheric cloud to form, and that's when the trouble really begins. Drifting around inside the polar vortex are reservoir molecules that have been bonded with chlorine atoms, and in doing so, preventing them so far from attacking ozone. When the polar stratospheric clouds form above Antarctica, chlorine reservoir molecules bind to the icy particles that make up the clouds. Once this happens, complex chemical reactions begin to take place that result in molecules of chlorine gas being released from the reservoirs. In this form, however, chlorine doesn't attack ozone, it just collects inside the vortex. All through the long dark winter, especially during July and August, the chemical reaction takes place on the surfaces of the polar stratospheric clouds, and they continue and more chlorine gas builds up inside the vortex. At this point, the stage is set for ozone destruction. All that is needed is a trigger to get the process going. That trigger comes in late August when the sun begins to rise. As the first rays of spring sunlight strike the stratosphere high over the frozen continent, conditions change very rapidly. The UV rays coming from the sun strike the chlorine-2 molecules inside the vortex. The molecules break apart, releasing billions of chlorine atoms that begin attacking ozone molecules and putting them back into oxygen and oxygen form. The result is a massive ozone destruction. Before long, so much ozone is destroyed inside the vortex that the ozone hole is formed. Ozone destruction continues and the hole remains until conditions in the stratosphere above Antarctica change. This usually begins in early October, when the continent and the air above it finally begin to warm up. The warmer temperatures in the stratosphere melt the icy particles that make up the PSCs, and the PSCs disappear, and the reservoir molecules that were bound to the icy particles are released. Free at last, the reservoir molecules bind chlorine atoms once again, and ozone destruction stops. Until recently, measurements of the spring ozone hole over Antarctica each year showed the overall size of the hole increasing. This graph shows up to 2010, where the total area under the graph has been increasing each year. 2004 was the highest. This year is an exception. This year we're predicted to be smaller than last year. So this may be the first year where we see a decrease in the ozone hole over Antarctica. This is thought to be the result of a reduction of the chlorofluorocarbons in the atmosphere. That said, it will take until 2050 for the ozone layer in the mid-latitudes to return to relatively healthy 1980s conditions, according to recent reports. Around the Antarctic, where the ozone layer is the most damaged, it will take until 2075. The human response to ozone depletion. In the 1970s, Malia and Rowland's prediction of damage to the ozone layer led to the reduction of use of CFCs as aerosol propellants. Confirmation of the Antarctic ozone hole and subsequent discoveries have led to a series of international agreements to reduce the damage. The most important of these is the Montreal Protocol, but there was also the London Amendments and the Copenhagen Agreements. To make things complicated, there are also naturally occurring substances that can destroy stratospheric ozone. They include hydrogen oxides, methane, hydrogen gas, and nitrogen oxides. Nitrogen oxides are part of the exhaust trail from jetliners who fly in the stratosphere. So jet propulsion on commercial airlines is also adding to the mix of things that can destroy ozone. In addition to that, methylene bromide, which is a pesticide, is also very stable and can get mixed into the upper atmosphere, as are sulfate aerosols from pesticides and burning of fossil fuels. Those types of chemicals can also be sent up into the stratosphere through volcanic eruptions. So what happens when the ozone is depleted? Well, a small amount of UV radiation is healthy for humans and other organisms. But for every 1% decrease in the ozone layer, the intensity of UVB radiation on the Earth's surface increases 2%. And we know that increased UVB radiation can cause several problems. Primarily, one that everyone's familiar with, is an increase in cancer rates. But it can also cause an increase in cataracts and other eye diseases, widespread ecosystem damage to the oceans and to areas underneath the huge holes, accelerated degradation and breakdown of various plastic products, and unpredictable climate change as well. Let's review this section of Chapter 17. In this section we talked about what stratospheric ozone is and why it's important, and how it's different than tropospheric ozone pollution. Why were the chlorofluorocarbons made and how they affect ozone in the upper atmosphere. We talked about extensively how the ozone hole gets created. Why was 2014 a special year for those measuring the ozone hole in Antarctica? What pieces of legislation were created in response to the ozone depletion in the stratosphere? And also, what are the complicating factors for natural ozone depletion? What are the negative effects of ozone depletion?